Good morning, students. Welcome to Functions class. In this paper, Functions, there are two important chapters. One is the nonlinear spaces and the Banach spaces. The other is the Hilbert spaces. So, for these two, I am using or I am referring two important textbooks. One is Introduction to Topology and Modern Analysis by G.F. Simmons, and the other is Introduction to Function Analysis by A.E. Taylor, and the other same with the same title, that is A.E. Taylor and David Seeley. You can refer any of the textbooks for functions. Okay, whichever you find easy, you can refer any of the study material or any textbook. So first let us take up the first chapter, that is the normed linear spaces. Normed linear spaces. So one part of this word is you are already familiar with. What's meant by a linear space you are already familiar with. So linear space means vector space. You have studied vector space in detail in your second semester classes. You have studied many more things in vector space and linear transformations. Here, so nonlinear space means it is vector space over the field. It may be real or complex, on which the norm is defined. So norm is just a formalization or the you call generalization of the intuitive notion of a length to the real vector space. A norm is a real valid function defined on the real space. So if you find the hierarchy of the spaces, mathematical spaces, so we can find that, say, first one is a very big space, that is a common. So topological space comes. Topological spaces comes. After that, so on this we will define a proper metric on this. So it becomes a metric spaces. And after that, say we will define a linear spaces and a norm is defined on that. So this becomes a normed linear spaces. And say on this nonlinear spaces, suppose if we introduce the inner product, if we introduce the inner products, it becomes inner product spaces. This is the hierarchy of spaces. Big one is the topological spaces, next is the metric spaces, next is the nonlinear spaces and the inner product spaces. And also here, so we will define another one, which is Hilbert spaces. Later we will discuss in the next chapter. Say now, so I will come to the proper definition of a formal definition of a norm of a vector. So as I said, norm is just a real valid function on the real linear space or the vector space. Say suppose you will have vector space. You know that vector space is denoted by the symbol V or X. So as your convenience, so suppose X is a vector space over the field F. You know that F may be so real or complex. F may be real or complex. So if F is real, it is a real vector space. X is complex, it becomes a complex vector space, that you know in your linear algebra classes. So now, so norm is, suppose X is, as I said, X is a real suppose X is a linear space. Suppose a function denoted by the symbol, say, so denoted by the symbol from X to, say, it is a as I said, it is a real valid function because it is the generalization of a length of a vector. So norm is just a real valid function defined on the vector space or a linear space X, such that it should satisfy the following conditions. First one is So norm is always so non-negative quantity for every x belongs to x. For every x belongs to x, norm is just a norm is a you know that norm is a okay a non-negative quantity. And the second one is norm of x is 0 if and only if x itself is 0. So means for non-negative for non-zero for so for non-zero numbers, so for non-zero vectors, so it is say norm of x is 0 implies x is 0 itself. Third one is norm of alpha into x is mod alpha into or absolute value of alpha into norm of x. This is third one. And the fourth one is norm of x plus y. You know that this is less than or equal to norm of x plus norm of y. This you know triangle. This is also known as the triangle inequality. This is the triangle inequality. Okay. So any linear space, say suppose x is a linear space, together with this norm is known as a normed linear space, normed linear space, normed linear space. This is the formal definition of a normed linear space. So now as I said, normed linear space maybe S becomes maybe not, it's every normed linear space is a metric space by suitably defining a metric. Say for example, if I define the distance of a function, distance function as d of xy is equal to norm of x minus y for every xy in x. If I define like this, then this normed linear space becomes a metric space. Normed linear space becomes a metric space. So we can take several examples of a normed linear space. Before that, say I'll give the examples of a normed linear space including this one, Banach spaces later. Before that, let us discuss another few important definitions. So you know that what is meant by a Cauchy sequence. What is a Cauchy sequence? You have studied in your analysis class. Cauchy sequence. Cauchy sequence. Suppose we have a normed linear space x with this norm. We can write x itself as a norm. It is understood that norm is defined on it. So suppose x is a normed linear space. Suppose we have a sequence xn. We have a sequence xn in x. We say this sequence xn is a Cauchy sequence if given epsilon positive, there exists that a positive integer, say a naught, such that for any pair of integers or pair of numbers m comma n greater than or equal to n naught, so the distance norm of xm minus xn is less than epsilon. So for every s, if xn is a sequence in x, then this sequence is said to be a Cauchy sequence if for each epsilon positive there exists a positive integer n such that m comma n greater than or equal to n naught implies norm of xm minus norm of xn is less than epsilon, or equivalently we can say that limit m comma n tending to infinity norm of xm minus xn is equal to 0. Norm of xm minus xn is equal to 0. So, and then the another important definition is, say, convergent convergent sequence. So what's meant by convergent sequence? As earlier we taken X to be a non-linear space. So we have a sequence xn in X. Then this sequence xn is said to be convergent and is said to converge to some point, say xn converge to some point, say x naught belongs to x. Converge to x naught belongs to x. That is, if given epsilon positive, there exists a positive integer, say n naught. There exists a positive integer n naught, such that n is greater than or equal to n naught. Such that n is greater than or equal to n naught implies a norm of xn minus x naught is less than epsilon. So the distance between the xn and x naught is less than epsilon. After certain stages, so xn is converging to x naught, or the distance between xn and x naught is negligible or very small. It follows that, say, limit n tends to infinity, norm of xn minus x naught is 0 if xn converges to x naught. Okay. So now Cauchy sequence, the other is the convergent sequence. You know that a very convergent sequence is a Cauchy sequence, but the converse need not holds true in general. In general, it will not holds true. So now suppose in a non-linear space X with norm, if suppose every Cauchy sequence converges, in X, then that non-linear space is said to be a complete non-linear space. Now, so let's come to the important definition of this chapter is the Banach spaces. Banach spaces. So Banach spaces nothing but, so a non-linear space which is complete as a metric space is known as a Banach space, or a complete non-linear space is called a complete non-linear space. A complete non-linear space is called the Banach space. A complete non-linear space is called the Banach spaces. Now, say we can in an Banach space we can have some inequality, like, say, or in a non-linear space, suppose X is a non-linear space. X is a non-linear space with norm. This is the norm I taken. Suppose in a non-linear space we have this inequality, say absolute value of norm of x minus norm of y is less than or equal to norm of x minus y. This holds for every xy belongs to x. So absolute value of norm of x minus norm of y is less than or equal to norm of x minus y. So you can show this very easily. So this is so you know that norm of x can be written as norm of x minus y plus y. But since it is a norm, so this can be written as norm of x minus y plus norm of y. Okay, can I write like this? Yes. So you can take norm of y onto the left. So this becomes this becomes norm of x minus norm of y is less than or equal to norm of x minus y. So you may call this as 1. You may call this as 1, equation 1. So similarly, interchanging the roles of x and y, we can see that similarly norm of y minus x is what? Norm of y minus norm of x is, norm of y minus norm of x is less than or equal to norm of y minus x, norm of y minus x, but norm of y minus x is same as norm of x minus y, norm of x minus y. So here I can write negative of norm of x minus norm of y is less than or equal to norm of x minus y. So this is, you can see, norm of negative of norm of x minus norm of y is less than or equal to norm of x minus y. You call this number 2. So from 1 and 2 we can see that mod of or absolute value of norm of x minus norm of y is less than or equal to norm of x minus y. Absolute value of norm of x minus norm of y is less than or equal to norm of x minus y. Okay. So this is one inequality that is very much needed to take up several examples in Banach spaces. Say, and so other definition I can take here, another definition which is needed now. So that definition is, suppose, say, you know what's meant by definition of continuity of a function in metric spaces. Here too we define the continuity of a function between any two nonlinear spaces. Suppose, say, x is a nonlinear space with the norm and y is another nonlinear space. So to distinguish between norm of x and norm of y, we can abbreviate this by, say, norm x and this by norm of y, means norm related to the space y, norm related to the space x. Suppose we have a mapping, f from x to y, f from nonlinear space x to the nonlinear space y. We say this f is continuous, at the point, say, x naught belongs to x. We say f is continuous at the point x naught belongs to x. If to each epsilon positive, you know that there exists a corresponding delta positive such that norm of x minus x naught is less than delta, norm of x minus x naught is delta, and delta implies norm of f of x minus f of x naught is less than epsilon. Norm of x minus x naught is less than delta implies norm of f of x minus f of x naught is less than epsilon. So this is the norm in y. So this is a norm in x. You can write this, or it is understood. You can leave. Then also you will understood that it is the elements in x. So it is a norm in x. It's the elements in y. So it's a norm in y. So and we say f is, this is continuous at the point x naught. Suppose we say f is continuous on the whole space x, means if it is continuous at each point of x, means f is continuous on x, f is say continuous on x. Continuous on x means it is continuous at each point of or every point of x. So next is, so alternatively this this definition can be restated as, say, suppose we have again this is x is nonlinear space with the norm x and y is another nonlinear space with the norm y. X is the nonlinear space with the norm x and y is the nonlinear space with norm y. A mapping f from x to y, in a mapping f from x to y is continuous at the point again x naught belongs to x if for every sequence if for every sequence xn in x converging to x naught, if for every sequence xn in x converging to x naught, the sequence f of xn in y, converges to f of x in y converges to say f of x naught. If the sequence f of xn converges to f of x naught, then we say f is continuous at x naught. That is, xn converges to x naught imply f of xn converges to f of x naught. Then also we say f is continuous at x naught. This definition also needed for our further study. And so in fact we can show that norm itself is, so the norm which defined on the vector space or the linear space. So norm is a real valued function, as you know. So this in fact is itself is a continuous function. Itself is a continuous function. If you want to see this, so I will use the second definition to prove this norm itself is a continuous function. Norm itself is a continuous function. Okay, say suppose we have a sequence xn. Say I will take a sequence xn in x such that xn converges to say x as n tending to infinity. Suppose xn converges to x as n tending to infinity. Now we consider the absolute value of f of xn minus f of x. You consider absolute value of f of xn minus f of x. So this is equal to f of xn means, according to our definition, say norm is a continuous function. We will define norm of say f of x is equal to norm of x. F of x is norm of x. So f of x is norm of x means here f of xn means norm of xn minus norm of x. But you know this is less than or equal to norm of xn minus x. But this tends to 0 as n tending to infinity. So as we have considered this n tending to infinity. So this implies what? F of xn converges to f of x. Means if you assume that xn converges to x, then f of xn converges to f of x. F of f is here nothing but the norm function. So norm is a continuous function on x. Okay. Next is, so these are some basic theorem that I am not going to prove it because this is a very basic thing. Say it states if x is equal to xn and y is equal to yn be sequences of scalars such that limit n tends to infinity xn is equal to x naught and limit n tends to infinity yn is equal to y naught, where xn naught and y naught are scalars, and if alpha is any scalar, then limit n tends to infinity xn plus yn is x naught plus y naught, and limit n tends to infinity alpha into xn is alpha n times x naught, limit n tends to infinity xn minus yn is x naught minus y naught, and if xn is less than or equal to yn for every n implies that x naught is less than or equal to y naught. This is the basic theorem that you may have studied this in real analysis class. Okay. Next is this is the case. Next let's take up the important, let's come to the important step, say where we are going to take up the examples. Okay. So now look here, say examples. Okay. First one is the very simple one. So I will take the linear space or the vector space to be just R, set of real numbers, or you take X to be set of complexes. So the simple norm that you can define it on X is, so for every X belongs to X, define norm of X. So or you define, so this is norm of X by absolute value of X or mod X. Define a norm on X by absolute value of X or mod of X. So then you can see that this, you know that this S satisfies all the condition of a norm, and so X together with this, X or R together with this becomes a non-linear space. Becomes a non-linear space. You can verify the properties of a non-linear. We can verify the properties of a norm for this. Then, so now already you know that the spaces R and C are complete spaces. R and C are complete spaces that you have studied in topology, and you have studied in analysis class also. R and C are complete spaces. Okay. In fact, so R is a complete space, R is a non-linear space, C is a non-linear space with respect to this norm, and it is they are complete spaces though. So this space R and C becomes a Banach spaces, complete non-linear spaces. So they becomes a Banach spaces. They are fundamental and very important. R and C are Banach spaces. So now let's come to R2, R3 and so on. In general, I will take up, say, Rn. X is Rn, the n-dimensional space, n-dimensional space Rn. X is the n-dimensional space Rn. Now here X belongs to, X means what? How X looks? It is a n tuple of real numbers. X belongs to X implies X can be written as, say, x1, x2 and so on, xn. So where each xi is a what? Real number. Where each xi is real. Where each xi is a real number. So n tuple of real numbers. So on this set X, that is Rn, I will define a norm by norm of X is equal to, this already you know it in metric spaces. Norm of X is equal to summation I is equal to 1 to n absolute value of xi square to the power of norm of X is equal to what? Summation I is equal to 1 to n mod absolute value of xi square to power of 1 by 2. So you can see that clearly this is a norm on X. If you wish, you can verify all the properties of a norm, that definitely it will satisfy all the properties of a norm. So our interest is to prove, to verify whether it is a complete non-linear space or not. Okay. So complete non-linear space means, so every Cauchy sequence must converge. So I'll take arbitrary Cauchy sequence, say xn be any Cauchy sequence. Let xn be any Cauchy sequence in, say, X means Rn. Xn be any Cauchy sequence in X. How this xn looks now? Xn is a Cauchy sequence means each element of xn is a n tuple of real numbers. Means the element xn will look like, say, x1n, x2n and so on, xnn, right? So this is n corresponding to this. Okay. So how do you write x1? Then the elements x1 as x11, x12, x21 and so on, xn1. So this is the first element in the sequence. Likewise, the nth element is xn is equal to x1n, x2n and so on, xnn. So here xkn general, xkn is the what? Kth coordinate of xn, the element xn. Here xkn is the kth coordinate. K kth coordinate of xkn. x to n is the second coordinate of xn, like xkn denotes the kth coordinate of xn. Okay. Now, so since this is we have taken xn to be a Cauchy sequence, xn to be a Cauchy sequence. So by definition of a Cauchy sequence, what will happen? So given epsilon positive, there exists a positive integer n naught such that m comma n greater than or equal to n naught, such that m comma n greater than or equal to m naught implies, so norm of xm minus xn is less than epsilon. Norm of xm minus xn is less than epsilon. So squaring on both sides, so this implies norm of xm minus xn whole square is less than epsilon. But norm of xm minus xn, according to our definition of a norm, this becomes, say, this implies summation I is equal to 1 to n norm of xm means here xim minus, so this is xin, okay. So this is not the norm, this is the modulus sign, whole square is less than epsilon square. This is also epsilon square. Okay. So now sum of the absolute values of these squares of these is less than epsilon square means each of them must be less than epsilon square because all are positive quantities. So let us say this implies norm absolute value of xim minus xin whole square is less than, this is whole square is less than epsilon square. Now this implies, since this is a non-negative quantity, so I'll say this is xim minus xin is less than epsilon for each I. So xim minus xin is less than for each I. So what are these xi's then? These xi's are nothing but the real numbers. Now, so for every m comma n greater than or equal to n naught, so we have xim minus xin is less than epsilon means what you can say xim, or in other words xin becomes a Cauchy sequence of real number, Cauchy sequence of real numbers, but R is complete. You know that the space R is complete. R is complete means every Cauchy sequence converges. Say this xin converges to say xi for each I. This holds for each I. So xin converges to xi for each I. So now our aim is to show that xn converges to x. So now we are going to show the sequence xn, what we have considered in the beginning, converges to the point x, where x contains the converging point of these sequences. Say x is the element where it contains n tuples as the converging points x1, x2, etc. up to xn. Now this is saying that this shows that the convergence is uniform. The convergence is uniform. So now the convergence is uniform means, by the definition of uniform convergence, what will happen? Summation I is equal to 1 to n xin minus xi whole square is less than say epsilon square. Or in other words, in the beginning you can take xin minus xi is xin converges to xi means xin minus xi mod of xin minus xi we can take is less than epsilon. So we take, since this holds for every element, I take the summation. So this implies, by definition of our norm, this is nothing but norm of xn minus x whole square is less than epsilon square. So this implies norm of xn minus x itself is less than epsilon. This means what? This means xn converges to x, which is element of Rn, because we have taken x to be the n tuple of the converging points where it is. They are all real numbers, means the point is in Rn. The point is in Rn. So we have a Cauchy sequence. We have considered that Cauchy sequence converges to a point of in Rn itself or in x. So we can say that, we can declare that Rn is a, or x, Rn is a complete nonlinear space. Complete nonlinear space. A complete, as you know, complete nonlinear space is called the Banach space. Therefore Rn becomes a Banach space. Banach space. Rn becomes a Banach space. So similarly we can show that Cn is a Banach space. Cn is a Banach space. Okay, this is just one two examples. We'll take further examples in the next class. Thank you.